So, we mentioned about trans, LES, DNS in the last lecture. Now we will go into what they actually mean and their strengths and limitations. Okay? There is no magic bullet. So effectively, each one has their own advantages, but they will also bring significant limitations as well. So keep that in mind. So, a little bit of recapitulation. As I told, I introduced a number of concepts yesterday, but we will keep on revisiting them. So, this is the turbulent kinetic energy we talked about. Yesterday we talked about energy spectrum as well. You might remember this kappa was wave number, which is essentially inversely proportional to the length scale of the eddy. So we talked about what eddy is, what's the typical schematic diagram of an eddy is yesterday. So the energy spectrum tells that within a small wave number range, how the energy is distributed. In other words, spectrum gives us the idea about how the energy is distributed, turbulent kinetic energy is distributed across different length scales of turbulence. And this is how it looked like. This is hopefully nothing new because you have already seen that yesterday. We told that energy spectrum assumes its peak value for this wave number, energy containing wave number, that is inversely proportional to the integral length scale of turbulence. So one of the things I mentioned yesterday, that integral length scale of turbulence is essentially the length scale where most of the energy is concentrated. And then what happens? The cascading process, which I told that the large eddies break down into smaller eddies. In doing so, it distributes its energy to its offsprings, and essentially that process continues until you come to this stage. So wave number increases in this direction, length scale decreases because wave number is inversely proportional to the length scale. And we told that at this stage, viscous action becomes extremely strong. It converts all the mechanical energy, heat energy. That's why this energy spectrum rapidly drops. Clear? Viscous action does not play any major role in this picture. Recall that all turbulent flows are high Reynolds number flows. Reynolds number signifies the ratio of inertial force to viscous force. Here, inertial force effectively dominates. Okay with that? In other words, if you want to actually visualize, here the turbulent eddies are energetic enough so that the inertial force associated with them can dominate over the viscous force. Okay? You can see as I increase my wave number, in other words, as I decrease my length scale, energy content is coming down. And when the energy content is low enough, at that time the inertial force and viscous force are becoming more comparable, and ultimately viscous action essentially takes over. Makes sense physically? So when you are looking at the spectrum, at least I know these things are a little bit abstract concepts, but at least mentally you can perhaps visualize what's going on. Happy up to this point? What happens in the case of, this is the spectrum of the dissipation rate of kinetic energy. epsilon. So if I T kappa, if T kappa is the energy, the spectrum of the dissipation rate of kinetic energy, which can be written like this. So it is 2 mu kappa squared times turbulent kinetic energy spectrum, and that is given by T kappa. It works like this. Okay? What really goes on here, that effectively here at this stage the value becomes the maximum and then it drops. Okay? So where this one drops, there the dissipation rate is the highest. Clear? In the case of direct numerical simulation, all the relevant length scales and time scales are resolved without any physical approximation. But that's good enough to say, obviously, if I'm carrying out direct numerical simulation, it's a numerical simulation, right? I will have a grid size, and that grid size is not zero, right? I have some finite grid size. Effectively, we resolve up to this point to this point. We don't resolve this process in direct numerical simulation. Similarly, we don't resolve this part in direct numerical simulation. But what I will argue that these plots are already shown in log-log format. This process is a really, really quick, sharp spectral roll-off. So by not resolving that, I'm not actually missing any interesting physics. Okay? So if I can, for all practical purpose, integrate my turbulent kinetic energy spectrum from this wave number, I will get my turbulent kinetic energy. If you have used log-log plot before, you know that smaller values are actually magnified, so this part is actually magnified and this part is really small. So instead of having 0 to infinity, if I put kappa ei to kappa ei, I am actually getting the whole of kinetic energy. And whole of turbulent kinetic energy is resolved in direct numerical simulation. Clear? Now, this is really an important diagram. Delta x is my grid size. Okay? All these things, wherever I have drawn the vertical line, this side is unresolved. So in the case of RANs, okay, in the case of RANs, the grid size scales with integral length scale of turbulence. So in RANs, effectively all the physics that's taking place from this line onwards is unresolved. When I'm talking about unresolved, that means your grid cannot capture those physical processes, but they don't disappear. They are still there. You need models to represent them. Once again, whenever I'm talking about model, that means you are actually going for a compromise, you are actually approximating something. How accurate your RAN simulations are depends on the accuracy of your model. Okay? Clear? In the case of DNS, you are resolving up to this point. Okay? You are missing this much, but you are not missing much. You are not really missing any interesting event. Clear? Happy with that? LES sits somewhere in between. So in the case of DNS, the grid size is going to be of the order of Kolmogorov length scale. We came up with Kolmogorov length scale yesterday. The grid size has to be actually, in reality, smaller than the Kolmogorov length scale. And in the case of LES, that effectively means your grid size has to be greater than Kolmogorov length scale considerably. But compare now between GRANS and LES. The first thing you will actually be able to appreciate, the extent of unresolved physics is relatively smaller in extent in LES in comparison to GRANS. Here, so I am already resolving some large scale turbulent motion using my grid in LES. Why I said large scale? Because smaller wave number means large scale, because wave number and length scale are inverse. Make sense? That also means that results for LES are going to be less sensitive to the modeling approximations in comparison to GRANS. Okay? The other thing is, as you go towards the large wave number, or in other words, small scale, turbulence starts to show a universal structure which is like homogeneous isotropic turbulence. We talked about that yesterday. Okay. So, if I actually develop some models based on homogeneous isotropic turbulence, which is the simplest type of turbulence that you can get, I can actually try to approximate this bit. Because by that time, the turbulence has already forgotten the large scale forcing or its configurational effects. It is showing an universal structure. That's the logic. Okay? Hopefully, just from this discussion, you can understand grid size is smaller in DNS in comparison to GRANS. That will translate in terms of more computational cost. If you keep the same domain size, that means you need more grid points in the case of DNS. Here, LES is going to be less expensive in comparison to DNS, but more expensive in comparison to GRANS. Clear? Accuracy improves from GRANS to LES to DNS. You are going to get three-dimensional resolved, spatially resolved, temporally resolved information in DNS. So you can almost consider DNS data as experimental data. Closest to truth you can get. I'm not telling that DNS is equal to full truth, because we will discuss later on that there are approximations involved when I am giving boundary conditions. But this is the closest to the actual picture, truth picture you can get using numerical simulations. And the kind of resolution you can get in DNS, sometimes, most of the times, is not achievable using experiments. It's extremely, extremely difficult to get three-dimensional velocity field resolved up to Kolmogorov length scale. Okay? Let me give an example. It's a statistically planar premix plane. Red part is product, blue part is unbound gas, is propagating like this. If you do GRANS, you will get a flattened surface. It's just a flat surface moving like this. Okay? DNS, this is the instantaneous claim front. You can see it is quite wrinkled. Okay. This LES gives you somewhere in it. If you compare between DNS and LES, you might be able to see the extent of flame wrinkling is smaller in comparison to DNS. And there is no wrinkling here because it's a statistically planar flame, as I mentioned. That means you are losing information from here to there, right? But that physical information doesn't go away. It's there, but you have to represent it by using models. Here, you remember yesterday I talked about taking a picture of an athlete who is running fast using your mobile camera. You get a smudged image because effectively during your exposure time you are averaging the picture. That's this. Here, now you invest in a very expensive DSLR camera with a very, very small exposure time. A sports journalist use, and then you get a sharp image of that athlete. So you have to invest money to buy specialized equipment, right? Cost-wise, exactly the same thing. If you actually invest more computational cost, then you can achieve that. Here, what happens, why RANS is important? Because out of all three methodologies, this is the cheapest one. And easily industry can adopt it as a result of that. This is extremely computationally expensive. The cost I will show later on is a strong function of turbulent Reynolds number. But it gives you highest possible resolution in 3D, most accurate. Out of these three, this is likely to be the least accurate. Okay? Large eddy simulation sits somewhere in between. Now, that was the situation until a few years ago, that LES is increasingly becoming popular in industry because of advancements in high-performance computing. People are using more and more LES in industrial configurations. When I used to work for General Electric in industry, if I told that I would like to do LES for a problem, there was no chance I would get a permission from my line manager. Now they regularly do LES. Not every day, but if required, they're ready to do LES. That was not possible 20 years ago. Okay? Even carrying out unsteady RANs, you had to win quite a bit of that battle. And I'm just giving G as my example. It's the same thing for these industrial houses, but they are adopting LES increasingly because high performance computing has become cheaper, more applicable. So direction of travel is going to be from RANs to LES in the future. Direct numerical simulations are mostly used for academic research, and they are generally used for very simple geometric configurations, because if you are dealing with complex configurations, computational cost becomes exorbitant. You can't have it. Does it mean it's useless? No, actually. The amount of physical insights that you can actually gain from direct numerical simulation, you can actually consider that data to be exact truth, and based on that you can actually generate high fidelity models for both LES as well as for RANs, equipped by the physical insights that you have gained from DNS data, and that essentially feeds into LES modeling and RANS modeling.
Do you mean to say that we can use some sort of validating purpose?
Yes. You can have the DNS data. You can actually explicitly Reynolds average it and extract the unclosed term that you want to model and compare that result with the model prediction. See how quick good the agreement is. If the agreement is not good, based on the physical understanding that you can actually obtain from DNS data, you can either modify your model or develop completely new model and validate it with respect to direct numerical simulation data. Even if you don't do that, you have several modeling options. You don't know which one is the best one. You can actually compare which one actually works the best under that circumstance. Okay? Hopefully the logic is clear that how these three methodologies are and how each one can actually contribute to our simulation activities in both industrial and academic settings. Hopefully that's clear. So, just to summarize, DNS does not need any turbulence modeling, but both LES and RANS need models for turbulence. And the accuracy obviously depends on the accuracy of the models. When I told that, that's not the full story. Accuracy obviously depends on the models, but modeling errors in both RANS and LES interact in a complex manner with numerical errors as well. So keep that in mind. Because whenever you are talking about DNS, LES or RANS, I'm talking about numerical solution of partial differential equations. When you are talking about numerical solution, there are huge approximations involved. DNS and LES have to be three-dimensional in nature. There is nothing called two-dimensional DNS, two-dimensional LES. I know there are papers available with that, but frankly that's junk. There is nothing called two-dimensional turbulence. Similarly, two-dimensional LES and two-dimensional DNS does not work. Okay. I think at this point, I need to indicate a couple of things. We talked yesterday about the syndromes of turbulence. Turbulence is fundamentally three-dimensional in nature. Okay. Both LES and DNS effectively gives you instantaneous picture of turbulence. That's why it has to be three-dimensional in nature. That means the kind of boundary conditions for simplification that you can use for dance context, for example, symmetry boundary condition, that's invalid in the case of DNS and LES. When you are telling symmetric boundary condition is symmetric in a statistical sense. Instantaneously, it is not symmetric. If you time average it over a long period of time, it will look symmetric. But if you are looking at a given snapshot, it might not be symmetric, and that's why these two will have to be three-dimensional in nature so that they can capture the instantaneous information. Clear? Similar thing exists for axis symmetry. Even if you have an axis symmetric jet, you can't use just half of the domain for DNS or LES purpose. It has to be three-dimensional. That obviously has implications on computational cost. You can't reduce the computational cost just taking half of the domain as well. Right? So, clearly, with that, let us actually estimate the computational cost. because maybe based on this discussion you are wondering why we can't do DNS for every problem. Let's see the computational cost. Effectively, if we integrate it using Kolmogorov spectrum, effectively this gives me this information. We came up with this yesterday. You will get exactly the same thing. A scales as u prime square kappa I. This one scales as 1 upon integral length scale. If you put those, you end up with this. Epsilon basically is given by this integral. We know that kappa di, because kappa di is much greater than in comparison to this, so I can approximate that integral by like this in this manner. Kappa di we know is approximately varies as 1 upon Kolmogorov length scale. This. Fine. If I now equate these two, okay, then from there I will get L over Kolmogorov length scale will vary as turbulent Reynolds number to the power 3/4. Okay. I showed the same thing with slightly different manner yesterday, but nothing new. We already have seen this yesterday. So let's say I have a box where I have in L number of eddies, big eddies, large eddies. So each large scale eddy has an integral length scale length. So my box size has to be NL times L. Clear? So number of grid points, roughly L box divided by delta x. So NL times L, my delta x will have to be smaller than the Kolmogorov length scale in order to have direct numerical simulation, because I want to resolve all physics of turbulence. Clear? So that gives me NL L over eta. We already got L over eta is given by RT to the power 3/4. So I can put it there. That's the number of grid size in one direction. So if I have three-dimensional simulation, it's cube of this. Clear? Now, lifetime of a turbulent, large-scale turbulent eddy, we also talked about that yesterday, L divided by U prime. Just I told that integral length scale is the length scale separation between two statistically independent velocity signals. In the same manner, this time scale is the time scale over which turbulence forgets about its history. So if you want two statistically independent signals, you have to actually wait for that time to get a statistically independent signal at a given location.
So that means you are telling that that is the time between time scale of means that the temporal distance between the when one single means scale vortices decomposes into two means that time you are saying.
Or alternatively, if you are looking at the statistics at a given point, in order to get to statistically independent signal, you have to wait for this much time. Clear? So in order to actually solve a partial differential equation, you can appreciate I have to give some initial conditions. That comes from the assumption, right? That I have decided that something is my initial condition. But after running, I want something which is realistic. So I have to run my simulation at least for this time. And that is a very optimistic estimation. not one, more the better, but at least one eddy turnover time. What's the smallest time scale of turbulence? Kolmogorov time scale. So if I am considering that my simulation will be spatially resolved as well as temporally resolved, my delta t has to be smaller than the Kolmogorov time scale. Does it make sense? So that gives me this result. So number of time steps required is the large scale time scale divided by the Kolmogorov time scale. So based on the scaling relations, we know the ratio between the large scale time scale to Kolmogorov time scale. Yesterday we showed it again in a different manner. That carries as I to the power half. Clear? So the total computational cost carries as the grid size times the number of time steps. Now you can see. Almost Reynolds number to the power cube, isn't it? Yes. Generally, you need to keep at least 3 eddies in each direction. So 3 cube gives you 27 sitting in front of it. At least 3, more the better. So you can understand, if you put instead of 3, 4, it becomes 64. How the computational cost goes up. What really happens? This is essentially the wave number range. Okay? If I consider this cube, I'm just looking at the cross section effectively. This is everything. Yeah. Kappa max is the maximum value of the wave number. It is given by this. Why n by 2? Because if you have done signal processing, it's a Nyquist frequency. Okay. So n by 2 divided by kappa 0 is 2 pi over L. When this goes there, you will get this kind of. What effectively you are looking for, that this is energy containing wave number, that means integral length scale. This is essentially kappa di, which is inversely proportional to the Kolmogorov length scale. This much computational effort, the yellow part for the dissipation range, and the blue part is remaining unresolved in DNS. Clear? So hopefully you can appreciate not much remains unresolved. These are the insignificant ones. Effectively, you can see most of the computational effort has actually gone to ensure this part is properly captured. So, typical time scale for homogeneous isotropic turbulence. N is the number of grid points in each directions. I've taken it from Ohm's book. At that time, computers were still doing gigaflop. Now we have teraflop. We are moving into exaflop. Okay? So the time will come down, but you can understand this is turbulent Reynolds number. So 94 probably 20 minutes. 6,000 industrially scale 6,000 can be achieved quite easily. 20 months. If you go for this kind of thing, 5,000 years. Obviously, if you are using parallel computing, you can scale it down. But you can perhaps understand how costly the simulations are, and combustion simulations. So if we put reacting flow on top of it, it becomes more expensive. How? But before we go to that, let's consider that we have compressible flow. No chemical reaction, just compressible flow. And I am actually time advancing using explicit method. I hope you understand what is implicit, what is explicit. And in the case of, let's say, subsonic flows, compressible, the Courant number criterion comes out to be roughly this. A is the acoustic speed, speed of sound. I have considered here that I'm dealing with subsonic flow, that's why I have actually ignored U in comparison to A. Okay? So, my delta T has to be smaller than this to satisfy Courant number criterion. If delta X is of the order of full motor length scale, I can actually come up with something which is given in this manner. So Mach number comes in play, and Mach number is defined as based on the RMS velocity fluctuation and acoustic speed. Now, if I use this one instead of this time scale, NT, you will find the scaling looks like this. Previously, here you had 11 over 4. Now it is Reynolds number cube. And the Mach number 6 in the denominator. That means if you are dealing with subsonic flow Mach number less than 1, it shoots up further. Clear? Let's say I'm dealing with reacting flow. Let's say premix flow. Very roughly speaking, the generic chemical reaction is given by reactants going into product. And I can define a variable called reaction progress variable. The name suggests as it shows on the tin, it basically shows how much progress of chemical reaction has taken place. This thing is defined in terms of, let's say, product mass fraction in this manner. Subscript 0 means the values in the unburned gas, infinity refers to the values in the fully burned gas. Okay? So you can understand when you are dealing with the fully unburned gas, this YP value is 0. So C is going to be 0. When you are in the fully burned region, YP value is going to be YP infinity, C is going to be 1. So reaction progress variable monotonically increases from 0 in the unburned gas to unity fully burned product. And the profile is given by this. Effectively, as the name suggests, this is called preheat zone. Here no chemical reaction takes place. This is where the chemical reaction actually takes place. That's the reaction zone, very small region. But heat diffuses from here to there. So the reactants are preheated before they actually come into the reaction zone. And here the products are formed. Roughly that's the picture. Okay. The important thing is I will need to resolve all of this physics if I am carrying out direct numerical simulation. Understood? I will use something, another one-dimensional number, which is given as Damp-Coulomb number. Effectively, it's a ratio of large-scale turbulent time scale, L over U prime, divided by the chemical time scale. Chemical time scale is given by the flame thickness over laminar burning velocity. So, let's say I need Q number of grid points to resolve the flame thickness. Typical value of Q varies between 10 to 20. If you are using simple chemical model, you can get away with 10. if you are dealing with more complex chemical mechanism, you have intermediate species, you have to actually consider the strong gradients of the intermediate species. The number of grid-point requirements goes up. Okay? So now, think about it. The size of my computational domain has to be delta thermal divided by Q, that's my grid size. And those delta thermal divided by Q times number of grid points is my box length. And effectively, my box length has to be greater than integral length scale of turbulence. And that gives me this relation as well. Now let's see, delta x needs to be smaller than this. And based on that, one gets this relation. Here K stands for another non-dimensional number called Karlovitz number. I'll explain what Karlovitz number is, but I'll tell you right now, Karlovitz number is the chemical time scale to Kolmogorov time scale ratio. Number of grid points now will scale NL, number of integral eddies I want to keep within the domain. Reynolds number to be 3, 4. But now you have Q, which varies from 10 to 20. Karlovitz number to the power minus half. So if I consider total number of grid points, it scales as this. On top of that, so if I consider just DNS of non-reacting incompressible flow, varies as this. Non-reacting compressible flow, varies as this. And if I consider compressible reacting flow, everything remains the same, but now I have an extra factor sitting here. Remember, this one varies as 10 at least, but can go up to 20. And then you are actually considering Q of that number. Karlovitz number gives you a measure of flame thickness to Kolmogorov length scale ratio. For industrial combustion purposes, Karlovitz number often remains less than 100. So effectively, if you consider this one is 10, this one has a value less than 100. This is considerably large factor coming here. So reacting flow DNS is considerably more expensive than non-reacting flow DNS. Just to give you an idea. As a result, very often in the past, combustion DNS was done either in 3D with simplified chemistry, or because in the case of simplified chemistry, number of equations that you are solving that can be reduced because you are actually not having too many species. Yesterday we talked about solving n plus 5 governing equations. If you reduce the number of n, computational cost goes down, right? That's the idea. Or sometimes by compromise 2D DNS, I still have my doubt whether 2D DNS is a right thing or not, because the fluid physics is very different in 2D. I told the cascading process, energy is distributed from the large scale to the smaller scale. In the case of 2D turbulence, energy flows from the smaller scale to the larger scale. Just the opposite thing happens. It's qualitatively very different picture, but just because of the cost, sometimes people need 2D analysis with simulations. Clear? But you can see a skeletal, that means bare minimum, propane-air reaction mechanism involves 27 species, 73 reactions. Typically will take this many time steps. And with present algorithms, it will take about 500 CPU years of top computer, this much terabytes of memory. So if I actually consider that, and in petrol engine, you have isotope air mixture typically has 800 species, 3,500 chemical reactions. If I start the simulation now, by the time the simulation finishes, IC engines are going to be of historical interest. You have no chance of getting anything there unless you actually make significant compromises. How to actually carry out initial conditions?
Sir, one question. So right now, the most advanced supercomputers, what are they solving regarding fluid mechanics? Which problem they are solving?
All kinds of problems. There is no kind of one particular thing. I think we have reached a stage with exascale computing, we can actually do DNS of lab scale problems. In the lab scale, at least combustion problems, turbulent Reynolds number is often of the order of several hundreds. You can actually match that kind of turbulent Reynolds number with DNS. The only problem is that those are going to be huge simulations. You can do one or two simulations, you cannot run a big parametric analysis. But if you want to carry out one particular simulation, it's possible nowadays. I routinely run for turbulent boundary layer plane wall interaction requiring 50,000 processors. That's more or less routine work. So in DNS, obviously you have to give an initial condition to start the simulation. And it makes sense that we have a good approximation to the turbulent flow solution. Good initial condition is to have a velocity field with a homogeneous isotropically compressible field. But when I'm talking about this kind of thing, it is just for a canonical configuration of the turbulence reports. For more detailed simulations, you need something more. So I'm talking about the simplest thing. If you consider homogeneous isotropic turbulence in compressible flow, divergence of velocity goes to 0. In the Fourier space, if you actually use this after Fourier transformation, assuming you have seen Fourier transformation before, if you take divergence of that, it will come out to be this, which effectively means the dot product of the wave number vector and the velocity vector in wave number space. They are orthogonal to each other. Okay? And then you can actually, in order to do that, what you can do, you can consider as if your wave number is in this direction, E3 direction, so that when you take dot product with the velocity in the wave number space, and this vector, it will give you 0. And velocity vector is even in this manner. Okay? E1 and E2 are the unit vectors in the wave number space. Okay? And these are the coefficients. They are essentially expressed in this manner. E kappa is the turbulent kinetic energy spectrum. Whatever you like, you can plug there, depending upon your choice of turbulent kinetic energy spectrum. This theta 1 and phi, and theta 2 here as well, and phi, are uniformly distributed random angles. So using a random number generator, you can generate those values. At that point, if I make another assumption that E1 lies in the xy plane, you can get this kind of relation for the unit vectors E1 and E2. And based on that, you get these expressions for the velocity components in 3 directions in the wave number space. And then if you do inverse Fourier transformation, you will get the velocities in the physical space. Now, if you have a jet, for example, you can actually specify your mean velocity with this kind of hyperbolic tangent profile. You know in a jet, effectively, the turbulent kinetic energy distribution is something like this. Basically, assume that you have in the shear layer. So you take this velocity fluctuations which you have generated throughout the domain, but stamp it with this kind of function so that you have this kind of profile. Okay? To begin the simulation. So please consider DNS in the same spirit of any numerical simulation, because approximations involved there. It is closest to the truth, but it's not truth, full truth. And this is one of the ways to actually generate initial information. There are other methods as well. Okay, but this is one of the widely used methods. Obviously, this will not necessarily work if you are doing for a boundary layer flow. In that case, you have to perhaps run boundary layer and allow it to evolve and then use that as your initial condition for doing something more. Yeah. Boundary conditions. Now, when I'm talking about boundary conditions, please understand that I'm talking about boundary conditions for Navier-Stokes equations. Navier-Stokes equations are known to mankind for over 250 years, probably a little bit more, but at least for 250 years in the way we formulate it. First useful paper on boundary condition for Navier-Stokes equation appeared in 1970s. You can appreciate how mature the field is. It's a complete mess, to be honest. What we are going to do in the context of DNS, especially compressible flow DNS, make do with the bad condition as much as possible, so that it does not affect the simulation results that much. This is true for RAMs and ABS as well, but often you do not think that way. Hopefully, after the lecture, probably you'll start to actually think that what I'm doing is an artificial thing. It does not actually happen in reality. So, 2 types of boundary conditions are there. One is physical boundary condition, which means periodicity. Although periodicity means essentially one side is basically linked to that another. This is not really a boundary condition, isn't it? Wall. You know exactly what happens at the wall. Velocities are 6. There is no ambiguity there. So that's easy. It gives rise to other issues that you have to resolve, the near wall structures and other things, but boundary condition wise, very well posed. There is no surprises there. Flux, if heat flux is given, or the wall temperature is given, you know what is there. No surprises. Soft boundary condition. This means that if I am solving partial differential equation, I need to keep certain number of boundary conditions, right? Otherwise, I can't solve those. But I don't have physical boundary conditions for all of those. So I have to invent something to actually solve the equations. One of them, in the case of compressible flow, is non-reflective boundary condition. That means whatever acoustic wave comes, it goes out of the domain. If I am solving a part of the pipe, let's say, when you actually put sometimes fully developed condition, then you del x equal to 0. That's soft boundary condition. Who told you that it has to be fully developed? Very often, if you don't have a long enough domain, you need to actually run for a long enough domain and take the results at this point. In the case of compressible flow, if I'm considering this much of the domain, and I'm telling this is my inflow velocity here. That's an artificial choice, because as soon as I told this is my inflow velocity, from the point of view of the acoustic wave, this surface actually moves with that velocity. It acts as a wall, but wall moves with that velocity. So what happens to the acoustic wave? It comes, gets reflected. But in real life, there is no physical boundary, right? If I have a pipe in an experimental condition, there is no physical boundary, right? If an acoustic wave can go out through that plane, right? So effectively, soft boundary condition is needed just to actually advance the simulation for mathematics purposes, but these are artificial conditions that I am imposing. And the outflow boundary condition which you always use in your simulations, probably now when you actually use that, just give it a thought that what you are doing at this point is not the real truth. You are actually compromising on something. And I don't know whether you have encountered that, but if you don't have long enough channel, and if you put that kind of zero gradient boundary condition, it will not converge, because you will have a fluorescent relation, and whatever you do, it's not going to work because it's not supposed to work. Okay? So, one of the important studies came in 1992. It is based on wave characteristic analysis. It's called Navier-Stokes characteristic boundary condition. That's why boundary conditions are specified with respect to wave amplitude variations with this kind of things, where AI are the amplitudes for different waves, acoustic waves. So all the waves which are coming into the boundary are specified. The ones which are going out from the domain through the boundary, they are specified using your already available solution. That's the idea. And they are evaluated based on locally one-dimensional implicit scheme. You can clearly understand how much assumption is made. Navier-Stokes equation is not valid for implicit. But you start with implicit, locally one-dimensional. Did I say turbulent flow is one-dimensional ever? No. But on top of that, then you put some extra boundary conditions for viscous effects on top of that. So effectively, this is how it looks like. This A1 and A5 are related to pressure and velocity. These are the acoustic waves. This is called entropy wave, and these are associated with the transverse velocities. So if you have this outflow boundary, these waves I don't need to specify because they are coming from the interior of the domain, but I have to specify this. Okay?
Sir, how U2 and U3 are considered? Say 3 and U2 in outflow is already given that data.
U2, basically telling the U2 and U3, the wave association, I'm telling you. The amplitude is related to that. They are not really equal to. Okay. The wave velocities are this. For the inflow boundary, effectively this, all the wave amplitude variations associated with them are specified. Okay. this one we don't need to specify because it's coming from the interior of the domain. Clear? Now, one important thing is if I want to make it completely non-reflecting, that is any acoustic wave which will come and go out of the boundary. That's what we want, right? Because if it gets reflected, that is an artificial effect. Unfortunately, specifying thing 0 will not work. Think about it. I'm assuming you have done compressible flow in your undergraduate. If you have done convergent, divergent nozzle kind of thing, that pressure at the outlet that plays a role whether you are a normal shock or rotation also. Yes. So whatever actually exists at the outside, that wave actually gives you the nature of pressure that should exist in your domain. If I tell no information will come from outside, simulation doesn't know what pressure to maintain within the simulation. You run the simulation, acoustic wave will go away without any problem, but your pressure will drift as the simulation goes on. What is the problem? If you consider ideal gas law or any state law, P equal to rho RT, if P changes, density and temperature will get affected as well. So I have to give some information so that I can actually retain the required pressure within my domain. And that's why, as a compromise, this kind of thing is done. A is like a time, it's not a time constant, but a characteristic constant. It's the required value. It's kind of a linear relaxation parameter. You actually retain the required value within the domain. As a compromise, that's called partially non-reflecting boundary condition. Okay? So, here is for Euler equation, if you are doing non-reflecting, this many boundary conditions are required. If you are talking about Navier-Stokes non-reacting, this many boundary conditions are required. If you are considering reacting flow, plus n because of the number of species. Specification of inflow boundary, however, is more difficult, because if you are having an inflow, I have to specify realistic velocity fluctuations at the inflow, right? In your actual experimental domain, if I call a part is inflow plane, that is actually evolving with time. And I can't just specify a certain kind of variation just like that. So the requirements are that realistic velocity fluctuations must be specified, velocity field must obey continuity if necessary. That means if it is an incompressible flow, it should be divergence free. It must have realistic temporal and spatial variations. So it has to have certain kind of integral length scale, that kind of thing. There are two solutions. You can run, instead of one DNS, two DNS. One, and from that precursor DNS you specify the inflow boundary condition for the second domain. DNS is already expensive. Running two DNS for one set of results, you can imagine how practical this is. However, it needs to be done for certain configuration. If you are doing, say, flame wall introduction, direct numerical simulation, you need to do a non-reacting channel flow simulation for inflow conditions. But most of the times, this is bypassed and use pre-computed direct numerical simulation data for specifying inflow. The idea is this. This is my solution domain. Okay. I have already pre-computed periodic box. At time t equal to 0, this plane and this plane are coincident. Right? And then you scan a plane through this box. And you use Taylor's hypothesis to get del u I del t. Scanning velocity is given by the required mean velocity at the inlet plus the 2k over 3, that's basically the RMS velocity. And using that, it's a periodic domain, so effectively if the plane goes out of this, it basically comes back. And that's how you specify the input. Realistic turbulent fluctuations. Clear? Idea? So, if you think that what really happens, let me explain. I put an acoustic wave, that's my initial progression. This is non-reflecting outflow. This is where velocity is specified. Inflow. I told if I specify velocity, immediately boundary becomes reflective because it's like wall which is moving. Acoustic wave will propagate in both in the outflow direction, inflow direction. This is with time. So it goes out cleanly through the outlet, non-reflective outflow. But it actually gets reflected magnificently, as you can see, as the inflow boundary. Then it propagates back to the outflow boundary, and then it escapes to the outflow boundary, and then you don't have it. Okay? This is just a toy problem, just to demonstrate. But in an actual compressible flow DLS, this flow goes on continuously. If you put turbulent inflow, generally experimental conditions for decaying turbulence, it follows this kind of power law with this kind of exponent, and you can see it more or less does reasonable a realistic decay on the unit. Now, that's not the end of the story. We have spatial discretization as well. The most accurate method is spectral method, which allows you to accurately calculate the derivatives. But spectral method will only work for the periodic direction. So if you have a domain which is periodic in all three directions, you can use spectral method happily. But if you have just an inflow and outflow, that breaks down. So essentially, very often you use specialized finite difference methods for actually approximating spatial derivatives. And they are very well suited for parallel computation. Easy to parallelize, but they need to be high order. General method, if I call f of x as fj, x plus delta x, fj plus 1, j plus 2, and plus 2x, then if I need for highest order accuracy for given order points, I will need these things. So effectively for nth order accuracy, I will need these many points. So nth order accuracy involves n minus 2 to n plus 2. Altogether n plus 1 points stencil for nth order accuracy. For fourth order accuracy, I have given an example here. You can try yourself later on. And using that table, you will get these coefficients for fourth order scheme. Effectively, the ultimate result will look something like this. Why is it important? as you can see, first order to second order, fourth order, error actually decreases significantly for higher orders. This is shown here just for a sample function, but qualitatively same behavior you will obtain if you use a different function. Okay? So if we can actually try to actually show, let's take this kind of e to the power kx, ikx as a sample wave thing. K is the wave number given in this manner. Xj is given in this way. So f dash x gives you this. You can analytically get the solution. Now, if we do second order scheme, we will get this. I should have got ik here. Instead, I have got something different, k dash. But k dash is this one. And if you look at, should have got k. So that means my wave number gets changed because of my numerical scheme. Right? Implication? For a spectral method, this is essentially my h times k, the actual wave number, and this numerically obtained wave number. For an ideal scheme, I will get this line. A spectral method will give you this. Second order, it starts to change. Fourth order, it change here. Third order changes here. If you increase to higher order, it will, this roll up will take place at higher value of wave number. Okay? In my DNS code, we use 10th order central difference scheme. So effectively, it rolls off here. Why is it important? Why can't we run DNS with second order scheme? The reason is the highest train rate is obtained at a Kolmogorov length scale. Okay. I have given you the estimates of velocity scale of the Kolmogorov scale, Kolmogorov length scale. If you can just put those velocity scale over the length scale, that will give you the strain rate, and you will see the highest strain rate is obtained at the Kolmogorov length scale. And if you cannot resolve that property, DNS is useless. And that's why you have to go for high order scheme. Okay? And this is another different method called a different scheme. I will skip that, but the procedure is described there. Temporal advancements. Very often you use high order round effector scheme. Because temporal resolution is important as well. So very often it is at least third order to fourth order functions. Downside of explicit scheme is that very often it is determined by the current number. Delta t is very small, you need to run for a long number of time steps. Whereas implicit time scheme means you can take any delta t size in principle as long, but this delta t obviously for DNS has to be small enough so that you actually resolve the essential physics. But it needs a matrix inversion for a large parallel system. When you are talking about a matrix inversion across 50,000 processors, it's a proper mess. Actually, very often people avoid that in going through the explicit system because that is more parallel computation friendly. As example of third order round effector scheme, so you were asking me whether I'll give you any code. Not given you any code here, but I have given you the algorithm so you can actually program it if you want. just to summarize this part, as you know, that DNS, the level of modeling, 0, get this kind of picture for a jet. LES, some degree of modeling is there, you get something like this. But you can see, you can using the sharpness of the image. And in RANs, there's quite a bit of modeling. And you got this kind of smashed image. Computational requirements, null. Strong function of Reynolds number. This is not really function of Reynolds number, it's function of your choice. What level of filter size you want to use. Okay? The filtering technique that I mentioned is often used for digital processing as well. They basically filter it in order to actually change the image. So effectively that's what we are doing implicitly in LES. So effectively filtering splits the quantity into the filtered form and the subrate fluctuation. The equations look like this. Very often the kinematic eddy viscosity is modeled in this manner. CS is called Smadroniski model constant. Although it's called constant, people change that value quite a bit. The theoretical value is 0.18, but you'll find in literature people use a wide range of values. So one interesting observation, filter does not anymore occur in the equation. Selection of delta to some extent is arbitrary. Effectively, generally delta, the filter width, that's why I told you never actually explicitly do filtering operation when you run large eddy simulation. Effectively, this delta filter width is proportional to the field size. Very often it is delta x times delta y times delta z, cube root of that product is taken to be the field size. And that basically comes in for specifying the kinematic eddy viscosity. Model equation looks similar to Dan's equation, but equation changes when the grid is changed. So the concept of grid independence study is not existent in LES, because if you change your grid, your model changes as well. You are changing two things simultaneously. Biggest advantage, large scales are computed, small scales are modeled, so you can see flow in a square track, all the secondary flows you are actually capturing. It's very difficult to capture using RAMs. You have to go for very advanced Reynolds stress closure to get these secondary flows. Potentially high accuracy. I already told small scales are expected to show universal behavior, and that's why it's easier to model them. Away from the wall, effectively you can see the spectrum. I think that the resolution is not coming well, but you should be able to see that on your hard copy. But you can see this behavior. If you look at the compensator spectrum, the spectrum behaves more or less identically away from the roll-off. So that's why away from the wall, LES is independent. Okay? It has been extremely useful, used widely nowadays. For example, engine manufacturers often use it for predicting cyclic variations in IC engines. I'm showing this as an example here. And you can see these are different realizations at different time instance. Velocity distribution without spray, velocity with spray, mixture fraction, that means how the mixture composition changes. All these things are done with large eddy simulation. But there is a capital part. nothing goes and I mean, every technique has its limitations. Wall treatment of LES is not as advanced as RANS. For wall-bounded LES, effectively LES boils down to RANS close to the wall. Okay? There's no difference between LES and RANS close to the wall. There are simulation methodologies called hybrid RANS LES. Basically means you do RANS close to the wall, away from the wall you do LES, and then you mask them. Transition, and there are other things as well, but these are the two major things. Nothing is standard yet. Okay? Some people say implicit filtering versus explicit filtering, implicit versus explicit LES, and subgrid model, suitable discretization techniques, and conventional grid independency analysis is not possible at all, because as soon as you change your grid, your model changes as well. So, effectively, there are different ways to estimate the error incurred in the case of LES. Typically, you would expect a good LES to resolve 80% of turbulent grid thickness. So, in the case of DNS, you actually resolve 100%. Here, it is 80%. And in RANS, you do not resolve anything. Okay? But there are different sources. Already, I talked enough about boundary condition specification. That is a source of error. But another thing, please understand, when I talked about 10th order central difference scheme, for central difference scheme, you need to go either side of the grid point to evaluate the. But when you are coming to inflow boundary or outflow boundary, you don't have the points in this direction, right? So as you come towards the boundary, then you have to resort to one-sided scheme. Okay? If I have to do one-sided scheme, I have to go this direction to get the information, right? When do you do that? If you consider your CMT lecture, only in the upwind scheme you go in the upstream to gather information, right? That's why the waves that they are coming from the interior of the domain, they are specified. The ones which are coming out from the outside of the domain, that is basically means if I go for one-sided difference scheme, then I'm violating that. I'm actually doing downward difference, and that creates trouble. You must have seen that in your CFT lecture. That's why they are specified. You do not calculate this on the information from the domain. So boundary can give rise to a problem, because at the boundary, the order of differentiation drops. So numerical error can happen, statistical error can happen, numerical error and modeling error, they really can actually interact extremely complex manner in LES. So this is a numerical error, which is ILES, which is the variable that you got based on the actual LES simulation, and this is the result that you got with a fine grid LES. And please understand, at this point, numerical error, essentially you are seeing to some extent. If you consider modeling error, fine grid LES and filtered DNS for the same, but that means for doing DNS simulation for the same problem, which is unrealistic for an industrial application. Total, hypothetically, actual LES, filtered DNS. That will have both the numerical error as well as the modeling error. Okay? think I have already mentioned that. I'll just talk about this one a little bit. When you consider that implicit filtering approach, which is the grid size, H, delta over H, delta is the filter width, H is the grid size, instance. If you reduce delta, it can converge towards DNS. If it is not constant, and if you reduce the filter width, it converges to some kind of hypothetical situation, not exactly DNS, because this value is not constant. Explicit, when this is not constant, it converges towards the filtered DNS. Usual grid refinement study using research on extrapolation is not possible because I am changing the model contribution as well. So, one needs some kind of special treatment using Taylor series expansion to estimate errors in LES. I'll skip this because this part is already written in a detailed manner in the.
Sir, for a single simulation, the Kolmogorov length scale is fixed. That does not changes.
Kolmogorov length scale can locally change. Depending in an industrial flow, it can change locally change. I have used this thing, standard grid with mesh size H. I have used U1 and F1, this convention. When we use the same grid, but model contribution is changed by a factor alpha. That means I'm just artificially changing the model by a factor alpha. It's written with that. Solution on a grid which is factored by beta times H. That means I have to change the grid spacing. Given as U3F3. And this is how these things are written. These are 3 equations, 5 unknowns. So, if I know these exponents n and n, these equations can be solved give these 2 conditions. As I have shown, 1 minus 2 and 2 minus 3 will give you this. And effectively, total error is given by this bit. A more conservative approach will give you magnitude of this individually plus magnitude of this individually. And if you consider a fully developed channel flow, RE tau friction Reynolds number 395 is Macronsky model. This is essentially estimated based on this kind of error estimation, which is done purely based on LES. By 2 stages, you run one LES, another time you actually change the model by a factor. Second time, you take the same model, but now change the grid size by a factor. These 3 LES for the same physical problem, and based on that, this solid line is estimated. And that when I'm talking about from DNS, that means we have run a DNS simulation for that particular problem and filtered it explicitly for the filter for which I ran the LES and subtracted and found the differences. And you can see, just based on LES, more or less captures the trend of the error. This is for channel flow, this is for plane and jet. Once again, you can see it reasonably captures the relative error. This is really a complex configuration. It's a swirl flow. This is a generic configuration for gas turbine combustors. But this is not done in reacting mode. This is just the non-reacting part. And you can see the errors estimated based on the error estimation methodology that I mentioned and estimated directly from DNS. So, to conclude, we talked about the fundamental concepts of DNS, LES, RANs. Hopefully, you can appreciate that there is no magic bullet. Each one brings its own limitations, but they have their unique advantages as well. We showed how costly DNS is based on scaling estimates. And we talked about quality assessment methodology or LES, which you can evaluate just basically running LES without actually going into the DNS simulation, because it is not easy to actually assess the quality of LES, because conventional grid independent study is not possible. The only thing I will tell that as a last remark, as a computational scientist, I really like this card. In 1950s, people didn't have computer, and most of the advancements in aerospace engineering took place because of conceptual thinking and simplified calculations in boundary layer. And basically what happens outside the boundary layer, what happens inside the boundary layer, matching them basically enable engineers to come up with the aircrafts which we use most of the time nowadays. So there is huge amount of mileage using this computer other than physical ones. So please, before you go into it, just because high-performance computing is becoming increasingly cheap, it is very tempting to actually run a simulation without thinking about anything. Please resist that temptation. Give a bit of thought before you run the simulation. If you are ever thinking about doing DNS, before you launch a DNS, think, why am I running this? What am I going to get out of that? I'm not telling you know all answers, because once you run a DNS, you will have a very valuable data set, and you can actually approach that data set from various points of view for various different analysis in the future. But you should have an idea that in the first place, why should I use so much of computational power to get something? Just to give you a context, if I am running a detailed chemistry direct numerical simulation for a simple fuel, let's say methane, air combustion, very often the carbon footprint of that simulation is equivalent to a transatlantic flight, a person's transatlantic flight. So with that, stop. Thank you.